Now we have learned what a unit of quantum information in a quantum computer is. Let's discuss in general how the process of implementing quantum computing works. Initially, we have some input that we want to transform. This transformation is in the classical form since we cannot have any other information in our world. To perform quantum manipulations on this information, we must load it into a quantum computer. For this, a coding process is used. In this process, we assign to the classical bit 0 or 1 the basic quantum state of the qubit 0 or 1. As a result, we get some input quantum state. Furthermore, this state needs to be transformed. That is, to carry out unitary evolution over the state. We'll discuss the evolution process in more detail a little later on. After the transformation, our input quantum state goes into the output quantum states. In the last step of the computation, we must measure the available output state to obtain classical information. This information will be for us the result of the work of the quantum computer. It is important to know that the described procedure is a model. In reality, the computational process is more complicated. In a quantum computer, as in the classical one, there must be ways to correct the errors that have arisen. We'll talk about it in the final module of the course. Now let's talk more about the most important part of quantum computing, namely quantum unitary transformations of input states. It can be said that a quantum computer is a device that can translate the input state into an arbitrary output one in a unitary way. This raises the question of how to implement such a device in practice. We know that the classical computer using logical gates. Gates are the set of elementary logical operations that together can perform complex transformations. Such gates include, for example, a 1-bit logical element NOT, which converts 0 to 1 and 1 to 0. There are also AND, OR, and other gates. It turns out that a similar principle can be determined in the quantum computing. Also, any transformation of a qubit can be represented as a product of elementary logical transformations. From the point of view of physics, such a product is a sequential application of elementary transformation to the input data. The main limitation that is imposed on elementary logical operators in the quantum case is that they must be unitary. It is important to note here that we are talking about unitary elementary operators on qubits and not about the method of obtaining them. As we will understand later, unitary operator can be implemented both in the unitary way and in a non-unitary way. As we know, there is an infinite number of unitary transformations, and therefore the question arises of how to choose the elementary logical operations that will be suitable for the implementation of universal quantum transformations. It can be proved that to perform universal quantum transformations, we need our quantum computer to be capable of implementing arbitrary 1-qubit transforms and 1 2-qubit control transform, which we will now discuss in more detail. As we found out, a qubit is a system with 2 basic states. That is, a qubit is a quantum system in a 2-dimensional Hilbert space. It is convenient to write the basic states of a qubit in this space in a vector form. State 0 is specified by vector 1, 0, 0, and state 1 by vector 0, 1. This vector representation is the most informative and is simple from the point of view of understanding quantum computing. Parallel matrices are introduced to describe the evolution of a qubit into 2-dimensional Hilbert space. The presented matrices have the following properties. Any parallel matrix squared is equal to identity matrix. The product of 2 different parallel matrices is proportional to the third parallel matrix. Parallel matrices are the basis for any 2x2 Hermitian matrices. In other words, any Hermitian matrix can be decomposed using parallel matrices in the following form. In this case, the modulus of the vector A must be equal to 1. Using parallel matrices, one can describe elementary logical operations. For example, using the matrix X, one can specify an analog of the NOT operation in the quantum case. Indeed, let's act with the parallel matrix X on the state 0. As a result, we get state 1. The converse is also true when the state 1 transforms to state 0. On the block sphere, this transformation is equivalent to the rotation of the state by the angle pi around the x-axis. Let's now consider the action of the Pauli matrix Z on a qubit. Multiplying the matrix Z by the vector of the qubit state, we see that this operation does not change the vector 0, but does change the sign of the vector 1. This will make a difference when using qubits in a state of quantum superposition. For example, the plus state, widely used in quantum computer, will go to the orthogonal minus state, and vice versa. There are infinitely many 2x2 unitary matrices, and therefore infinitely many one-qubit transformations. Let's take a look at the most general one-qubit transformations. And we have previously said any 2x2 Hermitian matrix can be decomposed in Pauli matrices. With this in mind, you can write any 2x2 unitary transformation as a matrix U. Here the exponent contains an arbitrary Hermitian matrix and theta is a parameter. Expanding the exponent in a series, as well as considering the properties of Pauli matrices, one can prove that the matrix U can be expanded in the form shown in the slide. The transformation we have obtained is universal, that is, any transformation can be decomposed in this form. This means that any transformation over a single qubit is a rotation of its state on the block sphere around the unit vector with coordinates ax, ay, az and the angle theta. This fact is very important because it helps us find those elementary quantum transformations that we need to build a universal computer. To implement any rotation of a vector in space, Euler proposed using 3 rotations. First, rotate by the angle alpha around the z-axis. Then, rotate through the angle beta around the x-axis. And finally, rotate by the angle gamma around the z-axis. These angles are called Euler angles. The choice of these angles allows you to bring the vector to any position. To find the matrices of these transformations, let's consider the general formula for the universal unitary transformation 2x2. To find the general form of the transformation of rotation around the x-axis, we must set the vector A' equal to 0, 0, 1. In this case, the transformation will be specified by the Pauli matrix Z. In matrix form, the transformation is shown on the slide. To find the transformation of rotation around the x-axis, we must take a double prime as a unit vector equal to 1, 0, 0. In this case, the transformation is determined by the X matrix and in vector form is given by the rotation matrix shown on the slide. Considering all of the above, any unitary transformation of a qubit can be written as a product of 3 matrices. Thus, we have learned that any transformation of one qubit can be performed if we can sequentially perform 2 rotation operations around the x-axis and z-axis. In this case, we do not even need to build elements with arbitrary angles of alpha, beta and gamma. We just need to be able to perform the rotation operation. The required turning angles are realized by choosing the appropriate interaction time. Let's now generalize to the case to the multiple qubits. When talking about 2-qubit elements, it is important to remember that we need elements that perform unitary operations. For example, direct analog of the 2-bit XOR operator cannot be implemented in a quantum computer since it is not unitary. In other words, it is fundamentally irreversible. With an output value of 1, we will not be able to determine what the values of the first and second qubit were in the input. So information is lost. Unitary quantum elements are always reversible, and therefore the result of the action of a quantum gate can always be inverted by another quantum element, a quantum element with an inverse unitary transformation. The simplest and most widely used logical 2-qubit element is a controlled NOT element. This element has 2 input qubits, control and target, respectively. The slide shows the characteristic designation of this valve. Here, the top line represents the control qubit and the bottom line represents the target qubit. The functioning of this element can be described as follows. If the control qubit is set to state 0, then the target qubit does not change. If the control qubit is in state 1, then the value of the target qubit is reversed. A formal record of this is presented on the slide. In the expression here, the first qubit is responsible for the control and the second qubit is responsible for the target. Here, CNOT gate can be described in another way, as the addition modulo 2 control and target state of qubits. In this case, the result of the addition is written into a value of the target qubit. The value of a control qubit does not change in this case. Another way to describe the action of CNOT operation is to give it an operator representation. The view of the CNOT operator is shown on the slide. It is important to note that in addition to the 2-qubit CNOT element, there are others. For example, in our course we will often use a 2-qubit controlled phase gate. This valve works as follows. If two input qubits are in state 1, then -1 will be added to them at the output. If at least one had a state of 0, then nothing will happen to them. This gate can be set by the general formula described on the slide. You can also use operator notation for this gate. The gates we have described are, in a sense, a prototype of the whole variety of quantum gates. This statement follows from the completeness theorem. This theorem states that any multi-qubit element can be composed of CNOT or C-phase and single-qubit elements. All operations are combined to implement one on another quantum transformation.